All right, so welcome everyone to today's Rencontres théoriciennes. Today we are very happy to have Sandipan Kundu from Johns Hopkins University, who is going to tell us about his recent work on chaos and quantum gravity.
Thanks, Miguel. I'm very happy to be here, even though virtually. So this talk is based on two of my recent papers from last year. To be completely honest with you, I never really understood quantum chaos. So these two papers were kind of written in an attempt to explain some aspects of quantum chaos to myself. So the idea is to learn as much as possible about quantum chaos directly from basic principles, something like what we do in Conformal Bootstrap. So please feel free to interrupt me whenever you have any kind of question. So we have a very intuitive understanding of classical chaos, mainly because classical chaos is almost everywhere. So a classical system is said to be chaotic if nearby trajectories in the phase space diverge exponentially fast if you wait for a long time. So something like this. For this lambda L exponent is known as the Lyapunov exponent. Let me not spend time on classical chaos because it's something that we all more or less understand. Instead, let me show you a very nice simulation that I found online, which demonstrates classical chaos beautifully. It's basically a system of two balls inside a spherical wall, which is perfectly reflective. So you cannot see two balls, you can only see one ball, mainly because the initial positions of these two balls are almost identical. There is only a very tiny difference. So you can only see one ball for first few seconds. Also, the two balls, they are slightly off the vertical axis. So let's see what happens if we start. Okay, so this is classical chaos. However, quantum chaos is a lot more subtle, mainly because our classical intuition is no longer sufficient to understand chaos in quantum systems. If we want to have a quantitative understanding of quantum chaos, the first thing that we need to figure out is the right observable that measures quantum chaos. Fortunately, this is a question that has been answered, at least partially. And in fact, there is no unique answer to this question. There are multiple observables that can be used to study chaos. But I'm going to mainly focus on a very specific observable. It's the out-of-time order correlators, also known as OTOC. These are correlators such as this. It's a 4-point correlator of two operators V and W. V and W, they're simple operators. The operator V is at t equals 0, but the operator W is at some other time t. And as you can see, this is an out-of-time order correlator. And it's a thermal correlator. So this rho is basically the thermal density matrix. And as you can see, the thermal density matrix is distributed throughout the correlator. Basically, this is a regularized version of the thermal correlator. This specific correlator was introduced by Maldacena, Shankar, and Stanford in 2015. But actually, this is basically a regularized version of the same correlator that Larkin and Ovchinnikov introduced in 1969. Since it was introduced by Maldacena, Shankar, and Stanford, this particular observable has been extensively analyzed and generally it is believed to be a very good measure of quantum chaos. Physically, what it does, basically, it measures the effect of a small perturbation made by the operator V at t equals to 0 on another operator W at a later time. So that's basically what it does. But if you want to, I'm not going to spend more like a lot of time on explaining why this is a good measure of quantum chaos. If you're interested, there are multiple talks, papers, lectures that are available explaining why this is a good measure. Instead, for the purpose of this talk, let's assume this to be a good measure of quantum chaos so that I can spend more time on the points that I really want to discuss. Okay. Now, when we study quantum chaos using this particular OTOC, and whenever I say OTOC, I'll always mean this very specific out-of-time order code. The signature, so our quantum system is said to be chaotic if this OTOC has the following behavior. Generally, this OTOC is always has this constant, like it's almost constant at early times, and this constant pace is basically the factorized value of the correlator. Then at the onset of chaos, somewhere here, this OTOC starts to deviate from its factorized value. Then at some point, the OTOC, for chaotic systems, the OTOC deviates significantly from the factorized value. So, and the time scale for that happens is the scrambling time. So this is one of the definition of the scrambling time. So after the scrambling time, generally the OTOC still decreases, and then for large time, generally it goes to 0. So which signifies the fact that all the information about the initial perturbation is completely lost at very late time. So this is a typical behavior of the OTOC for chaotic systems. And also in the time scale t, in the time scale which is much larger than the dispersion time t subscript d, but much smaller than the scrambling time, this OTOC also exhibits. It's expected to exhibit a period of Lyapunov behavior. So that means the OTOC has this particular form. So it gives there is this factorized pace, then there is this exponentially growing pace. And n here is an effective measure of the number of degrees of freedom. And so this looks very much like what happens in classical chaos. So this is, in some sense, is semi-classical chaos. This coefficient lambda L, in analogy with classical chaos, is also known as Lyapunov exponent of quantum chaos. It is all well known that this OTOC, even the regularized one, is a notoriously complicated object to compute. So it is rather remarkable that there is an upper bound on this Lyapunov exponent of quantum chaos. This is the famous MSS bound of Maldacena, Shanker, and Stanford. The bound basically tells us that the Lyapunov exponent must be bounded by 2 pi over beta. Conceptually, this is kind of remarkable. What it says is basically the fact that unlike in classical chaos, in quantum chaos, unlike in classical chaos, quantum chaos cannot grow arbitrarily fast. Its growth is bounded. There is one more reason why this bound is really significant. It has, for a long time, it is believed that quantum gravity is maximally chaotic. And this bounds provides a precise meaning to the statement maximal, to the phrase maximal chaos. This is basically, maximally chaotic systems are basically systems that saturate the MSS bound. However, there are many reasons to believe that this understanding of chaos is incomplete. Let me explain why. Let's again look at the OTOC with the same Lyapunov that exhibits this Lyapunov growth. So we have this factorized value, we have this exponentially growing term, which is the semi-classical piece, and then there can be this other correction terms. So the MSS bound is specifically a statement about this semi-classical piece. The MSS bound was derived from the fact that the full OTOC obeys some analyticity and boundedness conditions. But one can easily show that these two terms by themselves are not consistent with the same analyticity and boundedness condition. So what that means is basically these correction terms, they have to be there to make the full OTOC both analytic and bounded. However, we practically know nothing about these correction terms. So that's kind of unsatisfying because because these correction terms, they are fully quantum mechanical. And since we're talking about quantum chaos, it's kind of unsatisfying that we know nothing about these correction terms. We don't know if these correction terms are constrained or there are any restrictions that we need to impose on these correction terms. So we know practically nothing. So that's very unsatisfying. But if you think about it, you should expect that these correction terms should also be highly constrained. The reason is the following. It's not that any expansion that one can write down when resummed will lead to a function which is both analytic and bounded. That suggests whatever terms that can appear over here, they must be highly constrained. And this expectation is also supported by bounds from Bootstrap. There are certain CFT-Regi correlators that satisfies an infinite set of consistency conditions. And these CFT-Regi correlators are special cases of this particular OTOC. So this kind of suggests that probably we are missing infinitely many new constraints. Any question before I proceed?
Can I ask a few basic questions?
Yes.
So okay, start off with this definition, what is quantum chaos and so on. So you decided to work with the Otoc. So this Lyapunov exponent, does it depend on the specific Otoc that you're considering, for instance, or is it a universal property of the theory, or?
It depends. So like in most, like for example, in theories, holographic theories which are dual to Einstein gravity, it does not matter what kind of operators you start with. So all the examples that I know of, generally the exponent does not change, but the p factors, things like that can change. But I don't think there is a general argument that this should be the case.
Okay. And also, I mean, this definition of chaos involves turning on a temperature, right? I mean, the bound just goes away.
Yeah, that's right.
The temperature goes to zero. So, but okay, that's okay. You're just saying this is one definition. It's when you heat up the system that it will have this.
Yes. Behavior. Yeah, this is one definition. That's right. Like, so that's that can be a little bit unsatisfying because in classical chaos you don't need to do that. It's just like the standard, like you just change the initial condition and see what happens. But in quantum chaos, actually, it looks like having a temperature bath is kind of essential to even define quantum chaos, because like there has to be these thermal fluctuations which will make like things grow at later time.
I guess you could also consider just very heavy observables, probably that would mimic the effective temperature. No?
Yeah, exactly. Like you have to mimic that kind of effect. Yeah, exactly. Yes.
Okay. All right. Thank you.
Can I ask a question?
Yes.
Is it possible? So, regarding these other measures of chaos, for example, let's take the RMT type behavior that appears in spectral form factor at much later times than what you're considering here. Is it possible for a system to be maximally chaotic with respect to the Lyapunov behavior, but not maximally chaotic with respect to these other measures at much later times?
That's very possible. One of the issue of like talking about quantum chaos right now is basically there is no easy way to relate like one definition or one description of quantum chaos with the other any other description in terms of any other observable. So it's very possible that some of the effects may depend heavily on what observable we are choosing. So I would say the definition of maximal chaos, as I stated before, that's just one definition of maximal chaos, which is good enough for people who care about quantum gravity, let's say. But that, and actually, I'll discuss this more. And this is actually, even then, that definition is not unique in the sense that it's basically saying something about very early chaos growth. It does not say anything about like what happens at very late time. So it might be possible that like same initial kind of chaotic growth can lead to different like late time behavior.
Mm-hmm. Yeah, I'm willing to accept this definition for today to hear about your results. I'm even just wondering, since all the systems we know, or at least I know, that are maximally chaotic with respect to this Lyapunov criterion also exhibit those other RMT features later, I wonder if they're more tied together than it seems. Based on examples, they always seem to go together.
I can tell you one just very general statement, like just from all this, all the considered conditions that an OTOC must obey, there is no risk. Like the behavior of the OTOC at very late time, it's not dictated by its behavior at early times. So you can have like completely different behavior at very late times, even though you have a maximally chaotic phase in the early times. So like in principle, I would say like it's completely possible that there are different types of systems which look maximally chaotic in the early times, but like when you look at the spectral density, like it's different at it's not maximally chaotic. I don't see why that cannot happen at all.
Thanks.
Okay. So another question that
sorry,
yes.
I'm going to interrupt you again. But do you have in mind a large N theory? In all of what you say?
Yes. So basically, like the bounds that I'm going to derive, they don't depend on being large N. But generally, when people talk about quantum chaos, you kind of have to have a system with a large number of degrees of freedom. Otherwise, like making a small perturbation does not make any sense.
Okay.
So
is that also what?
Yeah. So
is that also what suppresses these ... terms on your previous slide? Is it like a 1/n type expansion, or?
Doesn't have to be. Like whatever I'm going to say, they are very general. Like the goal is to actually go beyond the 1/n terms.
Okay. Well, I'll wait and see. Thank you.
Okay. Yeah. So another question that should be of importance is basically to try to get a better understanding of maximal chaos. So as I said before, maximal chaos provides a bridge that connects quantum gravity to strongly chaotic quantum systems. So it would be nice to know more about maximally chaotic systems. For example, we know that maximal chaos is an approximate idea. That's because just from the analyticity and the boundedness condition, one can show that the emissions bound cannot be exactly saturated. By that, what I mean is that these two terms, this is what we get when you exactly saturate the emissions bound. But as I said before, this is inconsistent with the analyticity and the boundedness condition. So these other contributions must be there. Said in a different way, so maximal chaos is basically a statement about a leading growing term which needs to be analytically completed. this is very much like what we have in effective field theory. We generally have the low energy amplitude, which requires analytic completion. However, we practically know nothing about how to analytically complete maximal chaos. So obviously, I think this should be of importance in quantum gravity for the analytic completions of maximal chaos. So the goal is to address these questions, and to do that, I'm basically going to take the simplest possible approach that I could think of. It's basically, I'll start with basic properties of the OTOC that are well understood. And from there, I'll try to derive bounds on the OTOC in a systematic way. In a sense, this is very similar to what we do in conformal bootstrap. So it will not be surprising that some of the characters from conformal bootstrap will appear here as well in a natural way. So this is the outline of the rest of the talk. Let me pause for questions. If not, I'll. Okay. As I already said, I'm going to consider only thermal quantum systems with a large number of degrees of freedom and a simple Hamiltonian. So in such systems, there is a parametric separation between the dissipation time scale and the scrambling time. So dissipation time scale is basically the time scale above which all thermal two-point functions decay exponentially. In fact, above the dissipation time scale, all time-ordered thermal correlators also factorize. So, and actually, parametrically, the dissipation time scale should not be much different from beta, where beta is the inverse temperature. On the other hand, the scrambling time, it's scale as log n, where n is the number of degrees of freedom. So that's why there is a parametric separation between these two time scales when you have a large number of degrees of freedom. In the beginning, close to the dissipation time scale, the OTOC is basically practically given by or approximately given by the factorized value. Then it starts decreasing, and then it near the scrambling time, it deviates significantly from its initial value, and then it decays further. So that's how the OTOC behaves. So basically, the effect of quantum chaos becomes important only for times much larger than the dissipation time scale. So this is exactly the limit that I'm going to look at. I'm going to look at the OTOC in the limit where t is much larger than the dissipation time. So one advantage of this limit is that we don't actually have to worry about the initial transient effects. We can ignore them completely. So what are the basic properties of the OTOC? Again, this is the same OTOC that I showed you in the beginning. We have two operators V and W. They're simple local Hermitian operators, and rho is the thermal density matrix. So just from simple quantum mechanics, one can show that this OTOC as a function of complex time is analytic on the half strip. For this is reality, this is imaginarity, and the OTOC is analytic for when imaginarity is between minus beta over 4 and plus beta over 4. So in this half strip, the OTOC is analytic.
Sorry, so just one question. So by simple here just means that this parametric separation holds, right?
That's right. So basically, yeah, that's as long as there is a parametric separation, it's fine. Like so anything, whatever I'm saying, it's basically they apply to more general class of systems.
Yeah. Okay.
Even let me make one more comment. Even the bounds that I'm going to derive, they don't actually depend on the fact that if there is a parametric separation between two time scales or not. But when you try to implement these bounds, then these bounds will give you non-trivial results only when there is a parametric separation. But bounds, the bounds themselves, they're still valid. The second condition is that the OTOC satisfies the source reflection condition, where the bar represents a complex conjugation. Again, this follows from like simple quantum mechanics. There is nothing non-trivial going on so far. There is another more non-trivial condition. That's the statement that the OTOC is bounded by its factorized value on the boundary of the half strip for t greater than the dispersion time. Let me show you exactly where. So as I showed you, in this half strip, the OTOC is bounded on this boundary, these two boundaries. So this follows from some Cauchy-Schwarz inequality associated with some positive norm, which was derived by Maldacena, Schenker, and Stanford. So this requires unitarity. In other words, this is basically a statement that follows from unitarity. And just for the sake of completeness, this factorized value fd is basically written here. It's basically just the factorized two-point functions. Okay. So as I said, if I combine all these three, so in this half strip above the dispersion time, the OTOC is analytic, obeying source reflection condition, and it is bounded. And the MSS bound follows directly from these three conditions. Now let me make one comment. Actually, the boundedness condition that I discussed like a minute back is little weaker than the boundedness condition that was used by Maldacena, Schenker, and Stanford to derive the chaos bound. This bound is weaker. So in their original paper, they also assume that the OTOC is bounded by the factorized value even here. So that doesn't directly follow from the unitarity condition. That's a very mild assumption, but still it's an additional assumption. But I'll try to show you that that additional assumption is not actually required. So the MSS bound actually follows from these three standard or more reasonable assumptions as well. You don't need to assume this additional boundedness requirement. Okay, so let me now move on to new bounds on chaos. So before I do that, let me make a couple of comments. First of all, the actual derivation of these bounds are very simple. In fact, I was kind of surprised that nobody had derived these bounds before. In my opinion, the only non-trivial aspect of this derivation is the realization that there are other bounds on chaos beyond the MSS bound. Once you realize that, the actual derivation is very simple. So the fact that the MSS bound does not fully capture these three conditions, I give you some very hand-waving argument in the beginning why I expected that there were other bounds. But because this is an important point, let me give you a more rigorous argument which clearly shows that there are other bounds beyond the MSS bound. So this is basically, you can do that by deriving a dispersion relation for the OTOC. So what we have here is basically a contour integral of this quantity. We have the subtracted OTOC, we have this prefactor. And the contour is this one, which is closed at infinity. This integrand has a simple pole here at t prime equals to t. So we can evaluate this integral by from the residue, and that's what you get. We can also rewrite this integral by evaluating all this line segments. And in the limit where t is much larger than the dispersion time, this integration is not very important. It's basically something which is exponentially suppressed. And in that limit, basically, you end up with this dispersion relation. The integrand is strictly positive. That's because of the boundedness condition of the OTOC. So this is something one can derive in a very rigorous way. So once we have this dispersion relation, we can play the following game. We can try to construct D operators, which has the following property. When this D operator acts on this Sech function, it gives you something which is positive. If you can construct such a D operator, then you can go back and apply that D operator to the dispersion relation. So that D operator will hit only, since it's an operator acting on the variable t, it will only act on this Sech function here. So we should end up with, again, a positive integral. So that means if I can find a D operator which has this property, then that D operator acting on the subtracted OTOC must be positive. And that's how you can derive consistency condition on the OTOC. For an example, this is a very simple operator that you can check that satisfies this first condition. And then if you use the second condition, it basically gives you the MSS bound. So this is basically an alternative derivation of the MSS bound that follows from the dispersion relation and hence follows from the weaker boundedness condition.
Sorry, Sandipan,
yes.
Can you tell me what happens on your previous slides? Can you tell me what happens at large t in this dispersion? Large t prime, I guess.
Let's see. Sorry, let me go. For some reason, yeah, this one. Okay. So large t prime, it's basically if in the large t prime because of this term will dominate. That's why it will go to 0.
But aren't you precisely trying to show that f of t prime does not grow exponentially?
Yeah, because f of t prime is bounded. F of t prime is always bounded by the factorized value.
On the boundary.
It's an
because it's integrating on the boundary.
Yeah, it's so it can never grow exponentially. So that's the precise reason why the maximally chaotic OTOC needs decompletion, because it grows.
Oh, sorry, but I thought the boundedness only held at the edges of the strip.
Yes. So okay,
the contour lies.
No,
and
because it also goes to infinity, it also wraps the little line segment running vertically at very large t prime.
Yeah. So basically, even though the boundedness condition applies on the boundary, and obviously, if in a chaotic system that will always happen, in the middle, there will be at some place where the OTOC will also be bounded here because it's decreasing. So since it's an analytic function which is bounded on the boundary and also somewhere in between, it should be bounded everywhere.
Oh, no, sorry, this is a bit too fast. How do you know there isn't an essential singularity at with t prime real and infinite?
You mean this singularity?
No. At the bottom on the right. There's a little arc running at infinity, right, on the right that you are not drawing.
Yeah, this one, you mean?
Also knowing the behavior of the function inside the strip at infinity, and there is no bound, no?
No, like that's what I'm saying. So the bound is here, that I agree. But since f is an analytic function, so you can choose, like before you go to infinity, you can just choose any other slab over here. So that's where basically because of chaotic dynamics, f decreases, right? So f decreases from its.
No, but
sorry.
That's what you're. Where is that assumption coming in?
It's
an extra assumption.
It's not really an extra assumption. Okay, let me even I can do even better. It's basically, so even here, so there, that's where basically when you start the system or when you start the clock near the distribution time, it's without any big assumption, you can always show that f is not exactly bounded by the factorized value, but it's bounded by factorized value up to some order 1 over n number. So that means it's at least it's always bounded. It's not since it's bounded over here near the distribution time scale, and it's always bounded on the boundary. So it's a theorem in complex analysis that it has to be bounded at least by the maximum value over here.
I think you're neglecting one of the edges of your contour, but okay, we can let's postpone this discussion.
That there basically f can be at best it can be a constant, and this function decays there. So even at infinity, this thing in the numerator that can be at best it can be a constant, and the thing in the denominator it decays exponentially.
Okay, that's an extra assumption. I think you're saying that for the t prime with the imaginary part inside the strip, when you go to infinity, it's bounded.
No,
okay,
this is something you can show. It's okay. Yeah, it's not you can show it. It's not an actual an additional assumption. That's not actually true. You can show that. I probably I'll not be able to explain it right now, but yeah, you can show that. It's basically if f is bounded anywhere here, of which it is, then it's bounded everywhere. Okay. Or if you can you do?
But if it's bounded everywhere, then what's the MSS bound saying? Because it lowers it tells you something about that it cannot grow exponentially fast with a certain. Well, it can grow exponentially fast with a certain exponent.
Yes, that's right. But
that doesn't sound bounded to me.
It has a negative sign. So that in fact in the MSS bound, they actually that definitely require the fact that f is bounded everywhere inside this substrate, not just on the boundary, everywhere. That's basically from where the MSS bound followed. And the fact that it can grow exponentially, it comes with a negative. It's basically the factorized value minus exponentially growing term. So that's why it always decreases from the factorized value. And the fact that it cannot grow, it cannot be bigger than factorized value gives you a sign constraint on the coefficient of the growing term. So that's why it's negative. Yeah, so basically what I'm saying that the difference in the main difference between this and the MSS bound of the MSS bound, so they are basically they need to have the OTOC to be bounded everywhere inside this half strip. All I'm saying, we don't need that. Even if the OTOC is bounded by the factorized value plus some order 1 over n number, even that's fine. Okay. Any other question?
Well, I have a question about the next slide. You're going to get this equation with the differential operator. Do you need some assumption about derivatives of these functions, or anything like that?
Not really. The only assumption is basically this probably. So when I act on this equation by this derivative operator, I'm basically initially I have the operator outside the integral. I'm just taking it inside the integral. Basically, the only assumption is basically they commute. The integral and the differential operator. Okay. So now one can try to construct other D operators, and actually it's a very easy thing to do. Like if you can play with these equations, it's very easy to construct other D operators which obey the same condition. And in fact, it's very easy to construct an infinite tower of them, which are completely independent of this simple operator here. So that shows that there are infinitely many more bounds. But this is, in my opinion, this is not a very good way to derive bounds on the OTOC, because this way of deriving bounds depends heavily on how cleverly one can choose this D operator. Obviously, that's not a very good way to derive any kind of bound in any optimal way. The best way to derive these new bounds and organize them nicely is by defining moments of the OTOC. These are basically some integral of the subtracted OTOC with this very specific kernel. And the integration is along the imaginary direction for a fixed real time. So it's basically within the half strip, but along the imaginary direction. You can think of J, so there is this coefficient J, you can think of J as spin. And and within the half strip, this quantity is analytic. So this is just so far this is just a definition of the moment. And if you give me this OTOC, actually these integrals are very easy. One can compute them easily, and they can find these moments. So now from the definition, I have this integral over here, and from the analyticity condition, I can replace that by these two integrals. Again, there is this infinite piece, which you can convince yourself that also goes to 0 because this is an exponentially decaying function. So now, by using the source reflection condition, one can write down the following sum rule for the moments. So we have this integral where this quantity is positive. This is positive because of the boundedness condition. Now from this sum rule, well, one can write down the following bounds. From the sum rule, one can show that when J is an integer and non-negative, all the moments, they are both positive and bounded. Second of all, as you increase the integer spin, the moments must decrease for any t above the dispersion type. And finally, the moments must obey the log convexity condition. If you notice that the first two sets of bounds, they are strict inequalities. So they cannot be saturated. But the last bound can actually be saturated. This will be important later. So what are the implications? First of all, again, we can start with this functional form of the OTOC. And we can compute the moments. And if you play with this expression, you can easily convince yourself the positivity and the monotonicity condition require that the Lyapunov exponent must be bounded by 2 pi over beta. So that's a good sanity check. Now let's saturate the MSS bound. So now, again, I can compute the associated moments. So only the spin 0 moment is now non-zero. All the other integer moments are exactly 0. But that's inconsistent with the strict positivity condition. The moments has to be strictly positive. So this is a restatement. This is basically the same statement that MSS bound cannot be saturated exactly over any duration of time, however short. There always has to be these correction terms. Correction terms such as this. So just for simplicity, let's also assume that the correction term has the same exponential form. So we have the first term which saturates the MSS bound, the second term which is also a growing term. C1 and C2, there are some order 1 numerical factors, and epsilon is some small parameter that ensures the second term is subleading compared to the first term. This epsilon can be other factors of 1 over n, does not matter. It's basically a small parameter. Obviously, this is just an ansatz. This can have a more complicated form, but just to show you like what you can get if you assume some functional form. Again, you can compute the moments very easily. Again, you can perform the same exercise. That gives you an upper bound on lambda 2. So lambda 2 is bounded by 6 pi over beta. And there is also a sign constraint on the coefficient C2. And it's basically, and this pattern goes on for even higher order terms. So if you saturate the bound, this 6 pi over beta bound, then if you perform the same exercise, there is a bound on the next Ilya-Yapunov exponent, and this pattern goes on and on and on. And actually, so this is one kind of bounds that you can derive. But in fact, you can actually derive many more similar bounds, even when the OTOC does not saturate the MSS bound. So in that case, you can bound the you can derive precise bound on the coefficients of these growing terms. But I'm not going to show them here. If you're interested, please check my paper. Instead, let me focus on a different topic. So we have this. We have these new chaos bounds, which gives you MSS bound, which gives you other bounds on the subleading growing terms, which also recovers the CFT constraints that were missing before. But still, it does not feel like we have a better understanding. That's mainly because the physical meaning of these bounds in terms of the moments are not very clear. And it's also not very clear how to implement this bound. So if somebody gives me an OTOC, it looks like I have to check infinite set of constraints, which is a nightmare. Also, more conceptually, we are still thinking about chaos in a very perturbative sense. Even though the bounds in terms of moments, they are completely non-perturbative, the only way we can implement them is by imagining some kind of perturbative expansion of the OTOC. So it would be nice to go beyond this perturbative understanding. And because of this very fact, we still have no idea how to analytically complete maximal chaos, even though we have this infinite set of constraints. These are all difficult questions, but surprisingly, they are related to a much more simple question that can be solved exactly. So these problems are related to the problem of saturation of these new chaos bounds, which leads to the next topic, which is extremal chaos. So maximal chaos is when you saturate the MSS bound, as I discussed before. Similarly, one can define the extremal chaos in the following way. So we have this infinite set of constraints, and they contain a set of constraints that are strict inequalities. So these constraints cannot be saturated. But they also contain an infinite set of constraints that allow saturation. So the obvious thing to do would be to saturate all the inequalities that allow saturation without violating the strict inequalities. And that's how one can define extremal chaos. To begin with, it's not even obvious if this is an well-defined concept. For example, we have to satisfy infinitely many constraints, so it's completely possible that there is no consistent solution. But surprisingly, there is a unique solution to this problem. And that's what I call the extremal solution. It has this form. So this is completely fixed only up to some arbitrary parameter T effective, which is an arbitrary time scale, which one can think of as the effective scrambling time. the way to understand this T effective timescale is the following. For when T is much less than T effective, then the extremal solution coincides with the maximally chaotic solution, at least approximately. But this solution is well behaved even after the scrambling time. To show you graphically, this is how it behaves. So this red line is basically the extremal solution, and this dashed line, this is the maximal solution. So this is the dashed line is maximally chaotic OTOC. So in the beginning, two almost coincide. Then the extremal solution reaches T effective, after which it starts to grow again, and then it goes back to its initial value. So this is an analytic extension of maximal chaos, which is also bounded for real T.
This was unique.
Yes, this is unique.
Why can't you add things like which behave polynomial in T or something?
Then, like this is derived by saturating like infinite set of constraints. Like if you do that, like there is no like only thing that you can add. So this is unique up to terms that exponentially decay. So basically, so you cannot add any other term without actually going away from the saturation for at least one of the equations.
Are you saying that you can't add terms that exponentially grow, but just grow less fast than the leading ones, or that you can only add terms that truly decay?
Yes, that's right. That's right. That's right.
Which one?
The
first or the second?
Sorry, say that again.
Sorry, which of the two options was right? That you have to add terms which truly decay, or terms which are just exponentially suppressed compared to the leading ones?
No. The only terms that you can have, they have this form. I hope you can see.
Yes.
So it's basically T minus the dissipation time. So the only term that you can write, they are exponentially suppressed even when you are above the dissipation time. Like they don't care. Like so, when you are close to scrambling time, they are like way suppressed. Mm-hmm. They are exponentially decaying terms. Any other question? That's like this is so strict only because like you are saturating infinitely many constraints, and also there are infinitely many constraints that you have to obey. The strict inequalities. So there is no freedom. And actually, like I was surprised that even there is a solution. Like initially I thought like these are too strict restrictions.
Can you explain why the extremal solution doesn't look like loop corrections to Einstein gravity?
So, like I'll have a couple of things to say later. Probably the thing is that like the extremal, like I don't think quantum gravity has to be exactly extremely chaotic. Like there is no reason why it has to be true. So this is basically like still like even if you don't saturate these bounds, you can always like obey these bounds. In that case, like you might get something like this, right? Like that's still allowed. So this solution, the extremal solution, is basically a very specific analytic completion of maximal chaos, which like there is no reason why it has to be the case that everything is extremely chaotic.
It sort of breaks the equivalence between maximal chaos and strongly coupled that we've come to
I have a more precise statement that I will make at the end. Like definitely quantum gravity is related to extremal chaos, but in a like not in an exact way.
Okay, yeah, I'll wait till the end. Thanks.
Sorry, so why did you draw this curve like this? Are you making some claim that any Otoc has to lie below this extremal one?
No, I'm just like, you mean this one?
Yes.
This is just an example. For example, like you can definitely have analytic completion of maximal chaos which is close to zero for large T. So they are definitely allowed. So all I'm trying to say is basically like there is no reason why any analytic completion has to be extremal.
No, sure. What I'm asking is this extremal Otoc, in a sense, since it's the one that's growing?
Mm-hmm.
No, okay, maybe that's wrong. Well, is there some monotonicity or some bound on the value of the function that you can make, given this extremal function, or not?
Yeah, that's basically the final statement that I'm going to make today. Like there are things that you can say. Yes, definitely. So since it's an analytic function, it's not that like anything goes. Okay, so let me actually try to go to that point because I'm running out of time. So just some very quick comments. So because like the OTOC goes back to its initial value, so obviously there is no information loss in this extremal solution. But a physical system cannot be exactly extremely chaotic for the following reason. If you look at the extremal solution, you'll see that it has two singularities on the edge of the half strip. But a physical OTOC cannot have these singularities. So that's why a system cannot be exactly extremely chaotic. But these singularities are something that we are very familiar. These singularities are exactly the kind of singularities that we encounter in QFT. And we know how to remove these singularities even by like standard I epsilon regularization. If you do that, you'll get an OTOC which differs only slightly from the extremal solution. So
I understand, but then this extremal is not a good Otoc, right? Because it violates this boundedness at the end. That's the precise reason why a system cannot be exactly extremely chaotic. So because like these singularities cannot be there. So only thing, the best you can do is that you can just like remove them by I epsilon prescription, then everything is fine and you have an OTOC which is well behaved. But that's not the important point. The important point is these singularities actually have physical meaning. The presence of these singularities means that the extremal OTOC should be interpreted as a distribution. In a precise sense, what I mean is the following. Rigorously, one can show that any OTOC, that OTOC doesn't even have to be maximally chaotic in any region, can be written as an integral of the extremal solution with some density function. So for this extremal function over here is basically just the extremal solution, and this rho here is our density function. So one can rigorously show that the extremal solution provides this a spectral representation of all OTOCs. But obviously, at this point, this is not that surprising. But then, what you can do, you can actually find an inversion formula for the density function, and you can show that this is the inversion formula, which is very simple in this case. And because of the boundedness condition of the OTOC, this is strictly positive. So from there, to summarize everything, any OTOC can be expressed as an integral of the extremal solution, for the density function has the following properties. It has to be real, it is real, it is non-negative, it's a smooth function, and it's also bounded. And the main advantage of this spectral representation is that all the chaos bounds are automatically satisfied. So in my opinion, this is the right language to talk about quantum chaos, because you don't actually have to check all the chaos bounds. In this language, everything is all automatically satisfied. Just to give you a couple of examples, if you have a period of non-maximal chaos, so that the OTOC has this form, you can, using the inversion formula, you can easily compute the density function, and it has this particular structure. It decays. The dashed black line, this is basically the upper bound on the density function. So as you can see, at some point, the density function becomes inconsistent with the upper bound. So that means at that point, this dots here will be important. That's all it means. Similarly,
in this language, extremal chaos is represented by a single particle state. So that means basically the density function is exactly a delta function. And obviously, this is in tension with the boundedness property, and that's not surprising, mainly because, as I said before, the extremal solution has some singularities, because of which this is inconsistent with the boundedness property of the density function. So in a physical system, the delta function should be replaced by a narrow distribution. So this leads to the idea of small deformations of extremal chaos. So one can choose to remove the delta function and replace it by a narrow but smooth distribution, something like this. It can have a more complicated profile. So one can define in a very general way, one can define small deformations in a very general way. So it can be defined as follows. So the integral of the density function can be well approximated by the same integral, but now only in a very small window around T effective. Where the window has with delta T effective, which is much smaller than where the peak is. So that's why that's how one can define small deformations. And obviously, inside the window, it can have a lot more complicated profile, but in this definition, like everything is already included. The reason I'm spending any time talking about small deformation is the following. I can. So how much time do I have? I'm already, I think, at the 1 hour mark. So
yeah, you can take a few more minutes because there was a lot of questions and you started a bit later as well. So
okay, so without let me actually give you the brief argument. So now the reason why small deformations are important is as follows. Let's now look at maximal chaos, basically a system where the emissor's bound is approximately saturated over a long period of time. Over the same period of time, one can show that the density function is basically zero. It's approximately zero. Since it's an analytic function, rho can only have isolated zeros. So that's why it's very small, but it cannot be exactly zero. So something like the density function must be something like this. Excuse me. And so the density function should be very small, at least up to some point close to the scrambling time. But above the scrambling time, because of the boundedness condition, the density function is also very small. So the only place the density function can be significantly large is somewhere around the scrambling time in a very small window. And it's not just that it can be large there. It can be rigorously shown that it has to be large somewhere. And since it's basically zero here and zero here, so it has to be large within this window. The reason why it cannot be zero everywhere is the following. So rigorously, one can show that the integral of the density function is basically the coefficient of the maximally chaotic term. So whatever coefficient I have here, that's the one that I'll get if I integrate the density function. Since this coefficient is non-zero, that's why the integral of the density function cannot vanish everywhere. So if you have a system where there is a long period of maximal chaos, the density function doesn't have, like, it has to be large some here, and then it should go to zero as you go past the scrambling time. So in other words, all analytic completions of maximal chaos are small deformations of extremal chaos, because that is kind of dictated by all these chaos bounds and the fact that during a period of maximal chaos, the density function is vanishingly small. However, let me emphasize that the OTOC can differ significantly from the extremal OTOC. Only when we describe chaos in terms of these density functions, all the analytic completions, they are small deformations of extremal chaos. That's why I think this is the right language to talk about analytic completions of maximal chaos or even chaos itself. Just to give you an example, in Swarzyan theory, we know the OTOC as an expansion in 1 over n. And as a function, that OTOC is analytic everywhere within the substrate. So the OTOC looks something like this. And we even know the functional form of the OTOC. And from there, we can compute the associated density function. And it has a single peak near the scrambling time. But the width is of the order of, so this width is of the order of beta. So basically, like, it's a very narrow distribution around the scrambling time. One can check the same thing for 2D CFTs with large central charge. Again, the density function has the same qualitative feature. And in fact, the surprising thing is, in general, the density function can be a narrow distribution, but it can have a more complicated shape. But all the examples that I checked, it always has a single peak. So it always looks something like what we have for the Swarzyan theory. So now we can make a very straightforward conjecture. All theories of quantum gravity are strongly chaotic systems that are small deformations of extremely chaotic systems. So this should not be surprising at this point, because this follows directly from the first scrambling conjecture. So this is the last slide. There is an important, I don't think it's important, but it's an interesting observation that I should spend at least a minute on. Let's again look at the spectral representation. And we can think of doing this substitution. We can substitute T prime by energy, T by mu, and beta by 2 pi kb T, where kb is the Boltzmann constant. If you do that, you can check that this combination over here is exactly the Fermi-Dirac distribution. And and this spectral representation is basically some standard integral for a Fermi gas. So in some sense, Fermi-Dirac distribution is emerging naturally from quantum chaos, but I have no idea why this connection is there. It's completely possible that this is just an accident and there is no deeper meaning to this connection. But irrespective of that, this has some nice applications. So this connection provides us a way to use various mathematical tools available for the Fermi gas to analyze quantum chaos. For example, using some of the standard tricks of Fermi gas, one can actually derive some very general results about the OTOC at very early and very late times. If you're interested, please look into my paper. I'm not going to discuss them here. With that, let me conclude. So the most important point to me is that a lot can be learned about quantum chaos directly from basic principles. So the OTOC must obey an infinite set of constraints in any thermal quantum system with a large number of degrees of freedom. This infinite set of chaos bounds includes the MSS bound as the leading constraint. And there exists an extremal OTOC, which is a unique analytic extension of the maximally chaotic OTOC, saturating all the chaos bounds. The extremal OTOC provides a Callinan-Lehmann type representation for all OTOCs. And in my opinion, this is the right language for studying quantum chaos. And finally, I argued that all analytic completions of maximal chaos are small deformations of extremal chaos. And this should be of importance in quantum gravity. Thank you.
All right, let's thank Sandipan for this very nice talk. So, questions? So I have a question. So in the end, you just rewrote the original constraints in a different language, which made it obvious that to saturate these constraints, you should choose F to be this extreme of F. But so in essence, you started off with the Cauchy formula and you chose a particular kernel in the Cauchy formula, but there will be many choices for this kernel. But essentially, this is how you can derive this last formula of yours, right? You just choose this different kernel.
You mean which kernel are you talking about?
This formula, the dispersion relation that you have involving rho.
Oh, okay. No, yes.
This is essentially just Cauchy's formula, but with a non-trivial kernel. This basically this F extremal.
Yes, and also like you can you can derive this in a very simple way. So if you remember the dispersion relation that I discussed in the beginning, this is basically the same dispersion relation, just written in terms of the extremal solution.
It's the same, but it's just a change of variables.
It's not even a change of variable. It's basically just identification that the kernel there is basically this extremal solution. So it's just like it's basically after deriving the extremal solution, when I went back to look at the dispersion relation, it's basically the same function appeared there.
I see.
And exactly that's why like I could choose other kernel, then the rho will not have these properties. So since I'm thinking of rho as a density function, it should be like real and positive, things like that. So only when I have this kernel, rho has these properties, for which are basically like, because of these properties, I can say so much about like how the density function will behave for maximally chaotic systems, things like that.
Is this logic to say something about what happens before the dissipation time?
There are some
think of that as a UV completion of your Otoc from this dispersion relation. So you wouldn't be able to find the solution, but you might still constrain what happens before.
The only problem that I can think of is basically you have to make some stronger assumption about the OTOC. So the analyticity and the Schwarz reflection, they are general, but the boundedness condition can break down before the dissipation time. So
actually, in this context, by the way, the dissipation time is simply defined as the first time beyond which F is smaller than FD, right?
The dissipation time, you mean?
Yes.
Yeah. So that like in statistics in quantum like large N theories, basically not large N, like quantum many-body theories. Well, there is a precise way to define the dissipation time, but here it's very loose. Like you can take that definition, or you can just take a definition where basically F starts to just decrease below the factorized value. Like here, basically, that's why like none of the bounds depend that much on how you define these quantities.
But in the end, what's important is that it's bounded on these edges, right? So in this case, you know what it is. It's bounded by this FD, but okay, this FD is still some number that you don't know what it is. So if you could extend and just say it's bounded, but by some function that you don't know, you could still probably say something, no?
Yeah, actually, yes. So okay, I tried that at some point, exactly because like I wanted to understand what happens before the dissipation time. The problem is like if it's not bounded by FD but something else, you can still write this kind of bounds. But when you try to implement them, like for some functions, you'll see that like they are kind of trivial. So it's basically the bound on the boundary should be the same as like the factorized value. In that case, you get a lot out of these bounds. The reason is basically the OTOC also starts with the factorized value and then it decays, and it's also bounded by the same factorized value everywhere on the bounded edge of the strip. So these two statements should be the same. The same like factorized value should appear in both these statements. Yeah, that's one reason why I could not say anything about things before the distribution time. Like I'm not sure if the same factorless value will appear in the boundedness condition
If you just say everything is bounded above by a constant, this constant will be larger than FD, but then you just make it the same everywhere.
Mm-hmm.
Then well, I guess it would just be exactly what you've done now. It's just a redefinition of FD and TD, right?
Like the bounds will be exactly the same, but like I'm not sure their applicability. Like if somebody gives you some OTOC, then you'll see that like these bounds can be like completely obvious.
Well, you have to know FD, basically. It's the same thing. There's one constant missing, one piece of information. This you also need, always need, no matter what. So as I said, since you're just defining TD as the time where F is smaller than FD, from your point of view, it seems like this is just some number. So it's like a subtraction, basically. And this is an external input that you always need to give. So, but okay, it's not so interesting to pursue.
Can I ask a question? Yeah, hello. So these conditions you put on the density are sufficient to satisfy the bounds, but they're not necessary, right?
Which bounds?
The conditions you have on this page.
They are both necessary and sufficient.
No, they are not sufficient because you say that the delta function also gives a well, no, what I want to say, if the chaos is not maximal, then the integral of this function should be 0, so it cannot be always positive.
No, even when it's not maximal, the integral is not 0. Like, why do you say the integral is 0? There's no reason why the integral should be 0. Even for let me give you one example. Like even in this case, integral is not 0. It's not maximal anywhere.
I thought you said that the integral was the coefficient of the maximal exponent term.
Okay, so when you have a period of maximal, like in the beginning, if you have a period of maximal chaos, then the integral is exactly the coefficient of that term. So okay. If like it's non-maximal, then like that statement is not true. So it's not that like if you have other terms, the coefficient, like if the leading term is the term that saturates the MSS bound, then the coefficient of the leading term is exactly the integral of the density function.
But I could have said this function could have had such a term that the coefficient is 0, but then the coefficient should be the integral.
That's not how it works. So for example, if you have like other growing terms, not the maximally chaotic term, then that's like it's not that we are expanding. We have a full expansion. If you have a full expansion and you have a basis, then you can say that. It's not that. It's basically only thing that we know is basically the leading term. And if the leading term is, for example, if the leading term, like if you have the maximum term, but that's not the leading term, you have some other term which is the leading term, then that statement is not true.
Mm-hmm.
So it's a very specific set. If the leading term is the maximally chaotic term, only then the equation that I wrote was the correct equation. But otherwise, it's you can like in general you can write down other expression like I think I don't remember right now the integral of the density function can be related to some like non-zero object, but which is not this coefficient in general. But I don't remember that expression right now. But yeah, I think that you can derive something like that.
Okay.
I think it's basically the derivative of the first moment or something like that. I don't remember. Like you can write a very general statement of that kind. So yeah, these 4 conditions, they are necessary. Definitely, yeah. But it's also possible that like there is a possibility that there are other bounds on the OTOC that I am missing. In that case, like this is necessary but not sufficient. But I don't like. I'm kind of sure that like I exhausted all the possibilities, but even then, that like it's always possible that there are other more non-trivial bounds.
Could you just comment briefly on the relation this and the CFT? So this is some bound on the CFT 4-point function in Reggie kinematics.
Yes. Yeah. So it's basically let's see. Let me go back to. Okay, so this is so for the for CFT, you get very similar kind of bounds for the Reggie correlator in the limit when you take sigma to 0 first. There basically again you can derive bunch of some rules, something like let's see if I can remember. Okay, let me just write down the actual bounds. So if the Reggie correlator has this form, some coefficient CL plus sigma minus 1. Then these CL coefficients are actually all bounded, and they satisfy this similar kind of relations. So it's basically that's exactly how like the MSS bound is related to the coefficient, like the fact that the first term is always like cannot grow faster than 1 over sigma, and the coefficient is positive. There is a bunch of similar constraint on even on the higher order 1 over sigma terms. And if you like look at the exact bounds, they are exactly like this log convexity condition, monotonicity condition, and this kind of boundedness and positivity conditions. If you are interested, I can actually refer you to a paper, but yeah, these are like not that complicated. In fact, I think these follow directly from the like CFT dispersion relations that people are playing with. Like this kind of constraints follow directly from that. In fact, the spectral representation is kind of like the CFT dispersion relation in some limit.
Yeah, there's some. It looks like there's some similarities, but here you're in different kinematics.
Yeah, I didn't try to like connect both, but like I think like they look almost like similar, but like with some caveat. Probably those caveats can be fixed, but like I did not try, but it looked like almost identical. At least structurally, not like functions are different, probably like things like yeah, I did not actually try. Like they just looked very similar to what I saw before in CFT.
Last question.